Our loving God, we praise and thank you for the blessings you have given to us. Thank you for giving us a chance to continue learning amidst the pandemic that has caused a lot of changes in our lives. Bless us with the wisdom to understand our lesson and the joy to learn with our classmates. Bless also our teachers as they impart to us the value of learning. Help us to become children you want us to be. This we pray of Jesus Christ our Lord. Amen.
Good day, everyone. Our topic for today is all about the chapter 12, 12.8, the extrema of functions of two variables, to 12.9, Lagrange multipliers. By the way, I am Alvin Imbakay, and I am your teacher for today. Now, 12.8.1, definition of absolute extrema of functions of two variables. First, the functions f of two variables is said to have an absolute maximum value on each domain D, and the xy plane of there is some point of x sub 0 and y sub 0 and D such that f of x sub 0 and y sub 0 is greater than or equal to f of x and y for all points of x, y, and D. In such a case, f of x sub 0 and y sub 0 is the absolute maximum value of f on D. Second, the functions of f of two variables is said to have an absolute minimum value on each domain D, and the xy plane if there is some point of x sub 0 and y sub 0 and D such that f of x sub 0 and y 0 is less than or equal to f of x and y for all x and y and D. In such a case, f of x sub 0 and y sub 0 is the absolute minimum value of f on D. 12.8.2 Definitions of relative extrema of functions of two variables. First, the functions f of two variables is said to have a relative maximum value at the point x sub 0 and y sub 0. If there exists an open disk b of x sub 0 and y sub 0 are such that f of x sub 0 and y sub 0 is greater than or equal to f of x and y for all x and y and b. Second, the functions f of two variables is said to have a relative minimum value at the point x sub 0 and y sub 0. If there exists an open disk b of x sub 0 and y sub 0 and r such that f of x sub 0 and y sub 0 is less than or equal to f of x and y for all x and y and D. Illustration 1, Figure 2 shows the graph of the functions defined by f of x and y is equal to square root of 25 minus x squared minus y squared. Let B any open disk of x and 0 and r for which r is less than 5. For definitions 12.8.2, f has a relative maximum value of 5 at the point where x is equal to 0 and y is equal to 0. From definitions 12.8.1, 5 is also the absolute maximum value of f. So look at for the graph of figure 2 and the left side. So that's the graph of the figure number 2. Theorem 0.8.3. If f of x and y exists at all points in some open disk B of x sub 0 and y sub 0 and r, if has a relative extremum at x of sub 0 and y sub 0, then if x sub x of x sub 0 and y sub 0 and f sub y of x sub 0 and y sub 0 exists. If x if y if sub x of x sub 0 and y sub 0 is equal to 0, and f sub y of x sub 0 and y sub 0 is equal to 0. 12.8.4 Definitions of a critical point. If x of x and y exists at all points and some open dash D of x sub 0 and y sub 0 and R, the point x sub 0 and y sub 0 is a critical point of f if one of the following conditions holds. First, f sub x of x sub 0 and y sub 0 is equal to 0, and f of y of sub y of x sub 0 and y sub 0 is equal to 0. Next, if sub x of x sub 0 and y sub 0, or f sub y of sub 0, x sub 0 and y sub 0 does not exist. Example 1. Find any relative extrema of the function defined by f of x and y is equal to 6x minus 4y minus x squared minus 2y squared. Solution. We begin by finding any critical points of f. Differentiating, we obtain f sub x of x and y is equal to 6 minus 2x, and f sub y of x and y is equal to negative 4 minus 4y. Both partial derivatives exist everywhere, since f sub x of x and y and f sub y of x and y equal to 0. We get x is equal to 3 and y is equal to negative 1. Therefore, the only critical points is 3 and negative 1, and f of 3 and negative 1 is equal to 11. To test for a relative extremum at 3 and negative 1, we complete the squares in the expressions for f of x and y. F of x and y is equal to negative times x squared minus 6x plus 9 minus 2 times y squared plus 2y plus 1 plus 9 plus 2 is equal to negative times x minus 3 squared minus 2 times y plus 1 squared plus 11. Thus, if x and y is not equal to 3 and negative 1, f of x and y is less than to 11. Therefore, by definitions 12.8.2, f of 3 and negative 1 is equal to 11 is a relative maximum value by definition of 12.8.1. This is also an absolute maximum value. See the figure 5 for the graph of f, which is the paraboloid opening downward with its vertex at 3 and negative 1 and 11, positive 11, and the graph supports our answers. So look at for the graph in the left side of the figure 5. So that's the graph of the figure 5. Next is the 12.8.5. Theorem second derivative test. Let f be the functions of two variables such that f and its first and second order partial derivatives are continuous on some open dash of a and b and r. Suppose further that f sub x of a and b is equal to 0 and f sub y of a and b is equal to 0, and let d of a and b is equal to f sub x of a and b and f sub y of a and b minus f sub x and y of a and b squared. First, if has a relative minimum value at a and b if d of a and b is greater than 0 and f sub x of a and b is greater than 0 or f sub y of a and b is greater than 0. If has a relative maximum value at a and b if d of a and b is greater than 0 and f of x of a and b is less than to 0 or f sub y of a and b is less than to 0. Second, if a and b is not a relative extremum but if has a saddle point that at a and b and f of a and b if d of a and b is less than to 0. Next, no conclusion regarding relative extrema can be made if d of a and b is equal to 0. Example 6. A rare antique was the purchase in 1975 for $1,200. Its value was $1,800 in 1980, $2,500 in 1985, and $3,100 in 1990. If the value of the antique were to appreciate according to the same pattern through 2000, use the method at least squares to estimate the value of the antique in the year 2000. Solution. To find a regression line y is equal to mx plus b, we let x be the number of 5 years periods since 1975 and let y dollars be the value of the antique 5x years 5 times years since 1975. Thus, we have the data points given in the table 3. Table 4 shows the computations of the four summations appearing in equations 3 and 4 from the table. Summations of x sub I, where I is from 1 to 4, is equal to 6. Summations of x sub I, where I is from 1 to 4, is equal to 8,600. And summations of I of x, where I is from 1 to 4, is equal to 14. And summation to x sub I, where I is from 1 to 4, is equal to 16,100. With these values in n is equal to 4, we obtain from 4 and 3, m is equal to 4 times 16,100 minus 6 times 8,600 over 4 times 14 minus 6 times 6 is equal to 640. And b is equal to 1/4 times 8 open bracket 8,600 minus 640 times 6 is equal to 1,190. And equations of two regressions line S. Therefore, y is equal to 640x plus 1,190 for the year 2000. X is equal to 5, and for this value of x, y is equal to 640 times 5 plus 1,190 is equal to 4,390. Conclusion. The value of the antique is estimated to be $4,390 in the year 2000. So, on the left side is the table 3 and the table 4. So, that's the guide of the table of the example 6. We are now in the 12.9.1 theorem. Suppose f and g are functions of two variables with continuous first partial derivatives. If x has a relative extremum at the point x sub 0 and y sub 0 and f of x sub 0 and y sub 0 subject to the constraint g of x and y is equal to 0, and nabla g of x sub 0 and y sub 0 is not equal to 0, then there exists a constant lambda such that nabla f of x sub 0 and y sub 0 plus lambda and nabla g of x sub 0 and y sub 0 is equal to 0. To apply the method of Lagrange multipliers to find relative extrema of a function's f of two variables x and y subject to the constraint g of x and y is equal to 0. First, create the auxiliary functions of f of three variables x, y, and lambda for which f of x and y lambda is equal to f of x and y plus lambda g of x and y. Second, establish the system of equations obtained by setting the three first partial derivatives of f equal to 0. First, f sub x is equal f of x and y lambda is equal to 0, and f of y sub y of x and y lambda is equal to 0. F sub lambda of x and y lambda is equal to 0. Third, solve the system of equations in step 2 to determine critical points of f. And last, among the first two coordinates of the critical points of f found in the step 3 are values of x and y that give the desired relative extrema. Example number 1. Use the method of Lagrange multipliers to find the relative extrema of the functions f for which f of x and y is equal to 3x plus 4y minus 3 if the point x and y is on the circle of x negative 1 squared plus y squared is equal to 25. Solutions. We write the given equations of the circle in the form x squared plus y squared minus 2x minus 24 is equal to 0. To find the relative extrema of f subject to the constraint, we create the functions f. F of x and y lambda is equal to 3x plus 4y minus 3 plus lambda times x squared plus y squared minus 2x minus 24. We compute the partial derivatives f sub x and f sub y and f sub lambda and set the resulting function's values equal to 0. F sub x and 3 plus 2 lambda times x minus 1 is equal to 0. If f sub y 4 plus 2 lambda y is equal to 0, and f sub lambda x squared plus y squared minus 2x minus 24 is equal to 0. Observe from the equations 5 and 6 that x is not equal to 1 and y is not equal to 0. Solve these equations for lambda. We have lambda is equal to negative 3 over 2 times x minus 1 and lambda is equal to negative 2 over y. Equating these two values of lambda, we obtain 3y is equal to 4 times x minus 1 and y is equal to 4 over 3 times x minus 1. We substitute this value of y in equation 7 and solve for x. X squared plus 16 over 9 times x squared minus 2x plus 1 minus 2x minus 24 is equal to 0. 9 times 9x squared plus 16x squared minus 32x plus 16 minus 18x minus 216 is equal to 0. 25x squared minus 50x minus 20 is equal to 0. X squared minus 2x minus 8 is equal to 0. And x plus 2 times x minus 4 is equal to 0. And x is equal to negative 2 and x is equal to positive 4. From equating number 9 and 8, when x is equal to negative 2, then y is equal to negative 4 and lambda is equal to 1 half. And when x is equal to 4 and y is equal to 4 and lambda is equal to negative 1 half, the points negative 2 and negative 4 and positive 1 half and positive 4 and positive 4 and negative 1 half are therefore critical points of f. Thus, negative 2 and negative 4 and positive 4 and positive 4 are the only possible points for which f has a relative extremum, because f of negative 2 and negative 4 is equal to 3 times negative 2 plus 4 times negative 4 is equal to negative 5. And f of 4 and 4 is equal to 3 times 4 plus 4 times 4 minus 3 is equal to 25. Our relative minimum value of f is negative 25 and our relative maximum value is positive 25. 12.9.2 Theory. Suppose f and g are functions of three variables with continuous first partial derivatives. If f has a relative extremum where x is equal to x sub 0 and y is equal to y sub 0 and z is equal to z sub 0, subject to the constraint g of x and y and z is equal to 0, and nabla of g of x sub 0 and y sub 0 and z sub 0 is not equal to 0, then there is a constant lambda such that nabla f of x sub 0 and y sub 0 and z sub 0 plus lambda of nabla g of x sub 0 and y sub 0 and z sub 0 is equal to 0. The proof of this theorem, similar to that of theorem 12.9.1, involves showing that when neither nabla f of x sub 0 and y sub 0 and z of 0 nor nabla g of x sub 0 and y sub 0 and z sub 0 is the zero vector, they are both orthogonal to the surface g of x and y and z is equal to 0, which implies that nabla f of x sub 0 and y sub 0 and z sub 0 and nabla g of x sub 0 and y sub 0 and z sub 0 are parallel. This fact yields equations then, as theorem 12.9.1 did for a functions of two variables. Theorem 12.9.2 provides the following procedure for functions of three variables. To apply the method of Lagrange multipliers to find relative extrema of functions of f, their variables x and y and z subject to the constraint g of x, y, and z is equal to 0. First, create the auxiliary functions f of four variables x, y, and z, and lambda for which f of x, y, z, and lambda is equal to f of x and y and z plus lambda g of x and y and z. Second, establish the system of equations obtained by setting the four first partial derivatives of f equal to 0. First, f sub x of x, y, z, and lambda is equal to 0. If f sub y of x, y, z, and lambda is equal to 0. If lambda of x sub 0, if x and y, z, and lambda is equal to 0. If x of x, y, z, and lambda is equal to 0. And third, solve the system of equations, and step 2, determine critical points of f. Among the first three coordinates of the critical points of f found in step 3 are values of x, y, and z that give the desired relative extrema. Again, the 12.9.1 and the 12.9.2 theorem is the same process and the same procedure. That's all for today, and thank you for listening. God bless everyone, and goodbye.